has well, Matthew's already introduced Pavel, but just to reiterate, Pavel has been kind of at the center of this LLM revolution, having worked at OpenAI, XAI, and Anthropic, and having worked on O1 in particular. I also went at some point. Yeah, so real pleasure to have Pavel. Pavel is going to be at NYU, I think, from 2025. Yes.
Yeah, thank you so much. It's a real pleasure to be here. I will talk about our work on vector-strong generalization. This was joint work with Colin, Jan Hendrik, Bowen, Leo, Leopold, Ining, Adrian, Manas, Jan, Ilya, and Jeff, done at OpenAI as a part of the superhuman team. So kind of the main premise is that models are getting really smart. And of course, we discussed a lot of like caveats of looking at benchmarks. But if you look at any isolated task, then it's now like takes a very short time from stating a task to achieving human level on the task. So this is a nice plot where like for a lot of benchmarks, we track or they track the progress towards human level performance on the against time. And basically, you can see that the lines are basically almost vertical. Like on almost all of the benchmarks, we are getting close to human level performance. And as we discussed in our debate today, there isn't really a very strong reason to expect that the models will stop at human level for a lot of tasks. It's very possible that models will at some point be strongly superhuman. And that brings a challenge, which is that the model behavior is becoming increasingly difficult to evaluate. So once the models are really smart, it's also hard to tell what they're doing and are they doing a good job, which is important for training the models, for eliciting the best possible capabilities out of them, but also for safety reasons, for making sure that the models aren't doing something catastrophically bad and are doing things that are generally aligned with human preferences. So just to give an example, if the model is not very smart and it's only capable of doing very simple things like producing simple code for doing some kind of arithmetic, for example, then it's very easy for most humans to tell if what it's doing is right, but also if what it's doing is safe. But then, like, if the model is, like as we discussed, maybe the models will be producing, proofs to the Riemann hypothesis, which is by itself quite safe, probably. But if they are doing analogous things in terms of like producing huge code bases in new languages, new programming languages, it would be extremely hard for any human to evaluate what they're doing and to tell if what they're doing is safe in particular, and if we should be, like, for example, following the advice produced by the models. And so this is a pretty hard challenge. And I think if we do take the models getting smart seriously, then this can become more of an issue as we go forward. And even now already, like, I cannot supervise models on, for example, biology or chemistry or like any, pretty much any domain. Like you need domain experts. Companies are hiring like IMO Gold winners for, generating problems and things like that. We are already in the setting where we need experts to actually supervise the models. And this will only get harder and more expensive and, trickier. So the core challenge is that humans will at some point be weak compared to the models, and they will not be able to provide good reward signals or good supervision to the models. But the question is, how do we start studying this today? Is there anything we can already do? And we are trying to answer this by doing analogous experiments. So I guess traditional machine learning looks like this. We have a supervisor, which is like humans labeling the data. And the humans are strong relative to the model. The humans are able to produce labels which we can treat more or less as ground truth. And then the models are just trying to kind of understand the labels. And then the challenge that we envision having in the future is that the models will be smarter than humans. And we actually want models to do things that humans are not able to reliably grade or evaluate. And so we call this the super alignment problem. Can humans align super intelligent models? But today we don't have broadly super intelligent models. We have them on some very isolated domains, but not in general. And so today, instead, we propose to study an analogy, which is to have weak models supervise stronger models. So, for example, can GPT-2 provide supervision sufficient to elicit capabilities from GPT-4? So this will be this paper. And to make it more precise, we consider different tasks. And for each task, we generate the weak labels first. So to generate the weak labels, we fine-tune a weak model, a small model on the task. And then we use it to produce labels on held out data. So these labels will have a bunch of errors in them, and they will be biased in some ways because the weak model isn't able to fully fit the task. And then we train this weak to strong model, which is a strong, large model fine-tuned on the weak labels. And then we have a baseline, which is just a strong model, or the model, the same strong model, but fine-tuned on ground truth labels. And so then the question is, can we recover the performance of the strong model when we are just fine-tuning on the weak labels? So basically, we introduce this performance gap recovered metric, which is the ratio between two differences. The first one is how much better is weak to strong model compared to the weak model. And the second is how much better the strong model is compared to the weak model. So how much of the gap between the weak and strong model we are recovering when we are fine-tuning the strong model on the weak labels. And we want this measure to be as close to 1 as possible. If it's 1, it means that we were able to extract the best possible performance from the strong model using weak labels only. If it's at 0, that means that we are just imitating the weak labels. So yeah, ideally, we want this to be as close to 1 as possible. That's the goal. And so if we are able to succeed at this task, then that would mean that practically we can train superhuman reward models. So like in the same reinforcement learning from human feedback setting that is currently kind of dominant, we can train models, reward models that generalize from human level supervision to like superhuman capabilities. And that would allow us to train models to behave safely, even when humans cannot kind of judge their actions reliably. But also, from the capabilities perspective, it would allow us to elicit strong capabilities from the models. And then also, in addition to that, maybe we could have safety classifiers that also, like humans can label some data for is it safe behavior or not safe behavior. And then if we can generalize from human level to beyond human level, we can also use this like safety classifier to oversee models at testing. Okay, so this is the motivation. So now I'll talk about some results. So we consider 4 groups of tasks in the paper. The first one is NLP datasets. We have a collection of around 15 datasets, I believe, and we convert all of them to binary classification. These are just generic kind of NLP datasets from the literature. Then we also consider the reward modeling task, where the goal is to predict which of 2 completions to a given query is better. So this is the reward model that's used in the RLHF pipeline, and we are using the kind of ChatGPT dataset for training the reward model. We also consider the chess task. Chess is a generative task where we are considering chess puzzles. So there the goal is to, given a sequence of moves that leads to a certain chess position, predict the next best move in that position. And there is, by construction of the puzzles, there is only one good move in the position. We also do some experiments on vision, but I'll not talk about those at all in this talk. Okay, and for all experiments, we use a pre-trained GPT-4 model family. So these are base models. So without RLHF, these are pure language models. And there is a whole family of them, so spanning a range of big range of parameter sizes. So roughly from like GPT-2 level models to GPT-4 level models. No, yeah, these are like pure language models, so just next token prediction train. Yeah, and so throughout the talk, I'll be showing a lot of plots that look like this. So let's spend a couple of minutes learning how to read them. So here we are showing scaling plots. So the horizontal axis is the fraction of compute of GPT-4 corresponding to the pre-training of this model. So and the vertical axis is the test accuracy. And so it goes from like GPT-2 here to GPT-4 here. And if we look at the solid black line, that's the strong model performance. That's what we get when we just train or fine-tune the model of that size on the ground truth labels from the task. And then the colored curves correspond to different weak labels. So if you look at the lowest curve, the blue one, it's showing the performance when we use GPT-2 to produce the weak labels. So for example, this point is GPT-2 supervising GPT-2. So training a GPT-2 model on weak labels produced by GPT-2. And this point is training GPT-4 on GPT-2 labels, and so on. And then each of the different curves corresponds to a different weak model. So there is like models in between GPT-2 and GPT-3, and then GPT-3, and so on. So yeah, so basically we want the colorful curves to be as close to the black curve as possible. If they are close, that would mean we have high performance gap recovered. So we can visualize that like this, the performance gap recovered. So here, the GPT-2 trained on ground truth gets around 61% accuracy, and GPT-4 supervised by GPT-2 gets maybe 70% accuracy, but the GPT-4 trained on ground truth labels would get 90. And so we recovered around like 8% out of 30 of the gap in performance between GPT-2 and GPT-4. And so our PGR is something like 25%. So yeah, so we want this to be as close to 1 as possible. And yeah, and we will also be looking directly at PGR plots. So plots of performance gap recovered. That we want to be as close to 100 as possible. Okay, so now we are ready to look at some results. So first of all, these are the baseline results on the tasks that I described on NLP, chess, and reward modeling. And first of all, across the board, the PGRs are between 0 and 1. So we are recovering some of we are generalizing beyond the weak supervisor, but we are never recovering the full performance of the strong model. And yeah, the performance differs quite a bit between the different domains. So the best results are on NLP tasks, where all of the curves are always kind of trending upwards, the accuracy curves. So the performance improves with the strong model size for a given weak model. And the PGRs are also actually improving often with the strong model size. For chess puzzles, it's somewhat kind of intermediate performance. We are seeing some improvement compared to the weak supervisor, especially early on. So many of these curves are like initially improving, but then becoming flat. And the PGRs are actually decreasing with the student size. And then for the reward modeling task, it's the worst performance. The curves are almost all flat, meaning that the strong model doesn't do much better than the weak supervisor when we train it on the labels, the weak labels. And the PGRs are just uniformly very low. Okay, so these were the baseline results, and then we have a few different methods that we considered in the paper that can improve performance in this setting. So the first one is bootstrapping. So generally in the alignment community in particular, there is this idea that maybe directly aligning like the large superintelligent model will be very challenging, but maybe we should construct a sequence of models and align like an intermediate model and then use that to align the biggest model. And here we can actually test this idea in our setting. So instead of directly using GPT-2 to supervise GPT-4, we can construct this whole sequence of models and do multiple steps of this kind of weak to strong distillation. And we found that on chess, it actually helps on the chess puzzles. So here the baseline that I was showing you before is shown with the dashed lines, and then the solid lines are what we get through this kind of multi-step process. And we are seeing substantially better weak to strong generalization on chess if we do this bootstrapping. But it doesn't actually help on NLP, or it helps, but very little. And on the reward modeling tasks, it doesn't help at all. So this is not very satisfactory. And then for the NLP tasks, we actually have a much better method that works better. So specifically, it is using a confidence loss. So in general, if you think about what we are doing here, we are training strong models on the weak labels. And we are using actually soft labels for this. So we are using like probabilities outputted by the weak labels, and we are minimizing the cross entropy. So the ideal solution in this setting would be for the strong model to just perfectly imitate the weak labels to like predict exactly the same things that the weak model would do. So at least from the loss perspective. And this is actually not what we want, because we want the strong models to be able to disagree with the weak models, because like we expect the weak labels to have a bunch of mistakes, and we don't want the strong models to always follow the weak supervisor. And so a very simple idea is to add some kind of regularization to work the strong model's own predictions. So here we are just mixing the weak labels with the current predictions of the strong model itself. And we specifically, we have this coefficient alpha that goes from 0 to 1, and we are using some kind of modified strong model predictions. We make them like 0, 1, so we go from soft labels to hard labels, and we also class balance them. But like the important part is that we are regularizing towards strong model's own predictions. So if early in training the strong model starts to be confidently predicting for some data points something that contradicts the weak model, we are allowing it to like not get a big loss hit from that. And yeah, actually this is equivalent to just adding another cross entropy term, which is just increasing the confidence in the strong model's own predictions. So yeah. And so this method actually leads to quite substantial improvements on the NLP tasks. So here we are going from, in many cases, like if you look especially at the large model side of the plot, we are going from something like 20% PGR to something close to 80% PGR. So this very simple regularization term actually is very helpful in this particular setting on the NLP datasets. And it helps pretty uniformly across many different datasets. We have only a few exceptions. So specifically this one dataset, we are seeing that the confidence loss actually hurts the weak to strong generalization. But when it hurts, it's usually for datasets where we already had something weird going on. So for example, in this dataset, the performance when we just trained on the ground truth labels was already non-monotonic with the size of the model, which is quite unusual. And another unfortunate thing is that this loss still doesn't help on the reward models. So this is, again, not completely satisfactory, because I think the reward modeling task is the most real task out of the ones that we considered. And actually, none of the methods that we tried really help on the reward modeling task. Oh, okay.
Can we read something what is baseline performance for the supervision?
Yeah, I will look at some few shot, zero shot baselines later in the talk. Yeah, it's a good question. But I guess here it's a bit tricky, because yeah, this is a binary classification problem, and we are fine-tuning it with like a classification head. So yeah, but you can compute some kind of zero shot baseline actually, and yeah, it's a good question. Yeah, so these were the main kind of methodology things that we considered. I think like I'm not trying to say that this confidence loss, for example, is actually a method that we should be using for aligning superintelligent models, but it's more just directionally showing that there are interventions that can help in this setting. So we can go beyond just baseline performance. But overall, I think it's very much open what to do in this setting.
Wait, you said you're using a binary classification. And what's the strong model's own prediction when you use this for supervision?
Well, I mean, it's of the same model. So it's like you initialize the model with this classification head, binary classification head, and then it's that prediction that we're using as a strong prediction. So it changes over training. It's not like a zero-shot prediction. Yeah. Okay, so now we'll discuss some kind of understanding phenomena type results that we observed about the models. So first of all, as we already mentioned, in this weak to strong setting, we are training the strong model to imitate the weak model. And intuitively, yeah, the best thing that the strong model can do from the loss perspective is imitation. And what that means is that there can be some overfitting to the weak model's mistakes. And interestingly, in this setting, overfitting can happen within like before one epoch of data, because it's not overfitting to like the specific training data points, but it's overfitting to the bias in the labeling. And we actually do observe that. So here on the plot, we are showing performance of the strong model when trained on the weak labels as a function of training time. And you can see that for a lot of these curves, they are, or some of these curves at least, they peak very early in training, and then they actually become worse. And so yeah, so this is, there is overfitting happening. We do see it in practice. And actually, if we were able to do early stopping and stop at the best possible time, then we would do quite a bit better, in particular on this reward modeling task. But the challenge is that we cannot actually, we don't assume that we have ground truth labels on any kind of validation set. And in that case, you cannot really do early stopping. If you do early stopping with respect to the weak labels, then then the best thing to do would be to just wait until the end of the epoch, because we only do one epoch. So I think this is a pretty open question, how to do early stopping in this setting where we don't assume we have access to very high quality labels. But yeah, if we were able to do that, then on the reward models, we would actually see much better PGRs, performance gaps recovered. Okay, and another result that was pretty surprising to us when working on this was this. So again, like we are training the strong models to imitate the weak models. And then we can measure how good the strong models are actually at imitating the weak models. So we can measure this agreement metric, which is a fraction of data points, or the test data points, on which the weak models, the strong models agree with the weak supervisors after training. And so we plotted here, so both for the full data set and also separated by data points where the supervisor is correct or is wrong. And what we see is that, so first of all, the agreements are somewhat high. They are above the weak accuracy, pretty much always, the weak model accuracy, but also they are pretty far from 100%. And what's most surprising to me is that they become worse with the model size, the student size. So here, this is a case of inverse scaling, actually, because we are training the strong models to predict the weak labels, but they are becoming worse at it as the size increases. So like a GPT-3 size model is better at predicting GPT-2 labels than a GPT-4 size model. And this is especially true on the mistakes of the supervisor. And this is largely probably the reason why we are seeing this weak to strong generalization right now. It's because the strong students are just not able to imitate the mistakes of the weak supervisors very well. And this is actually a potential disanalogy to the case that we care about, and I'll talk about that a bit at the end of the talk.
Sorry, so this is not the case with the loss that had the term that allowed the small, like the strong learner to agree with itself, right?
Both with, so actually, good point. I forgot to say that with the confidence loss, this is even more the case. So with the confidence loss, that's the solid lines here, and it becomes even worse at imitating the student, but that's kind of what we want, I guess, from the confidence loss. But even without the confidence loss, for the dashed lines, you can see that all of them are sloping down. So like this is GPT-2 trained on GPT-2, and this is GPT-4 trained on GPT-2. And so the larger the model is, the worse it is at predicting the weak labels, even though that's what we train it to do exactly. Okay, so another question is, So generally, why can we even expect this to work? Why can we expect the strong models to generalize better than the labels that we train them on? Is because we can expect that the true kind of generalization is very salient in the strong model. So if it should be easier for the strong model to generalize in the correct way than to kind of imitate the weak labels. And so we can try to probe whether this is the case for the current experiments that we do by trying to understand the salience of the generalization. So how easy it is to actually get good performance out of the models. And at least on the NLP datasets, it's actually quite easy. So here we show the zero-shot baseline is the bottom curve, and then this is what happens when we fine-tune on the ground truth labels, and this is what happens when we provide 5 examples with ground truth labels. So you can see that even with just 5 examples, for the largest models, they are already doing pretty well on the task. You already recover like most of the gap between the zero-shot performance and the kind of full fine-tune. So in a way, these NLP tasks are just very salient to the models. And this makes sense. Like, for example, if we consider a task like sentiment analysis, where the goal is to predict, is this comment positive or negative, then the true generalization is very salient for GPT-4. It does understand whether the comment is positive or negative, while predicting GPT-2 labels can be much harder for GPT-4. And then we can also, actually, we can repeat the kind of whole experiment with doing few-shot prompting instead of fine-tuning. So that's what we show on the left. And we kind of get qualitatively similar results. So when we prompt the strong model with a few examples, 5 examples of weak labels, it gets us somewhere in between the zero-shot baseline and the prompting with ground truth labels. So the results don't really depend that much on whether we are fine-tuning or probing prompting, few-shot prompting. And another point is actually, interestingly, for the largest models, prompting with weak labels can do better than fine-tuning on the weak labels. So if you look at this curve, this is what happens when we fine-tune on weak labels from a certain model. And this curve is what happens when we probe, a few-shot prompt with the same weak labels. And actually, prompting can do better, but we are still recovering better performance with the confidence loss. And so if we believe that this salience to the model of the kind of concepts of the true generalization is very important, then we can try to improve it by unsupervised fine-tuning. So if we revisit the RM task, the reward modeling task, we can try to just use all of the completions and fine-tune our base model on all of those. And hopefully, some kind of representations emerge that are helpful for this task. So we tried that, and it actually does help. So here we are not using any of the labels at all. We are just fine-tuning on all of the prompts completions from the dataset before we are doing the actual weak to strong RM training. And we see that that does improve both the strong model performance as well as the weak model performance, but also it improves the PGRs. So we are recovering more of the gap in the performance when we do this. So it does look like the salience of the true generalization is helpful, at least for weak to strong generalization. And so if we actually combine all of these tricks, we do this generative fine-tuning, and then we do cheating early stopping, then we are getting something like 30 to 40% PGRs on the reward modeling task, which means that it's at least somewhat promising on the reward modeling task as well. But again, the cheating early stopping is not something that we can generally do. We cannot call this a method because we don't assume access to the ground truth labels. Okay. So there are some limitations to this work. So first of all, almost everything that we considered is a single forward pass classification. It's a very simple toy setting, and also currently like the most exciting things in the LLMs are things involving chain of thought, like O1 models, for example. And we are not covering this at all in this experimentation. It would be very interesting to see if, like, an O1 style model, for example, could generalize from a weak supervisor and do things beyond the supervisor. And then another thing is that for the types of weak to strong generalization that we observe, the datasets that we consider, like they are pretty much absorbed in the pre-training, or like at least the skills that are required are absorbed in the pre-training. And then probably the reason we see this weak to strong generalization is because the model kind of saw extremely relevant tasks during pre-training. But then for this generalization beyond like human level, we actually expect that there will be something a bit more intricate, like the model gets interesting representations from pre-training, and then maybe and for somehow the true generalization to some very complex task is just salient to the model. But yeah, this is not covered by the current setting. And then I think the main disanalogy is that like the thing that I described about the imitation, basically that the current models are just pretty bad at imitating the mistakes of the weak models. But in the future, we expect that for a superhuman model, it would be very easy to just imitate what the supervisor would predict for this task, probably. And that makes it a much, much more challenging setting. Right now, we get some weak to strong generalization by default, but in the future, this may not be the case. In terms of open questions, I think like one is just, are there methods that can work really well in the setting and the setting is, just to summarize, that the labels are very imperfect. They are biased and they are coming from like, and we want to generalize in ways that don't agree with the labels. So I guess we can try to come up with some methods that have certain desired properties, such as we don't want to just imitate the weak supervisor. We just want to generalize the intent from there. We want to find generalizations that are natural or salient to the model. And maybe we can come up with some kind of consistency properties that could be helpful here, that maybe like predictions on problems that are equivalent should be always the same. And maybe there are some methods that can work really well here. Another question is, how do we trust the results without having the ground truth labels? A related question is, how do we do early stopping? So because if we assume that we don't have any ground truth labels, we just have the weak labels, and then the strong model provides some kind of predictions, how do we know if those predictions are good at all? Or is the strong model just imitating the weak labels, for example? And then there are quite a few kind of scientific questions, like why are the results on the reward models so much worse than the results on chess and on NLP datasets? And also, what makes performance better on some datasets than on others in general? What kind of capabilities or behaviors will be easy and what will be hard to elicit? And another question is, right now in the experiments, we used weak labels with errors. So we just like use the weak models to make predictions on all of the test data points, and we train on all of those. But you could imagine doing things like only including data points where you are extremely confident in the labels, for example. So instead of weak to strong generalization, you could try to do some kind of easy to hard generalization. So maybe like humans are capable of providing really reliable labels on very simple cases of a certain task. And then would that be better than this setting where we provide unreliable labels on all examples in the task? So I guess to summarize, we consider this weak to strong generalization setting, which is a somewhat unusual setting for machine learning, where the labels are extremely unreliable, but they're not just noisy, they're actually biased in interesting ways. And we find that in the setting that we considered, often the weak supervisors can elicit substantially better performance than their own performance. But still, we are pretty far from eliciting all like the full potential of the strong models in the settings. And there are many open questions. Yeah, that's it.
You you have weak labels from GPT-2 and so on. If you calculate kind of what are the levels?
So I think you can see, like basically in these plots, if we look at them, then this, like, for example, for this curve, right, the weak label accuracy is here. It's like 60%. And then all of these models are trained on those labels. So yeah, so it differs by the for this particular data set. Yeah, so it differs a lot. Some data sets are easy, some data sets are hard. So yeah. And they're not, I think it's important that these are not just noisy, corrupted labels. They can be very biased in certain ways. Mm-hmm.
Do you know that over your head some like examples of setups where like this not having access to ground truth labels is like natural restriction?
You mean for like the current modern day machine learning, or yeah? No, I mean I think in the future, like the problem that we're thinking about is something like, in particular, I think this was largely motivated by safety questions. So like, is this code safe, for example, that the model outputs? And then maybe you could reliably say if the code is safe to run for like short programs, but like for very long programs, it's very hard. And yeah, I think that's, you can have pretty unreliable labels from humans on this task. Or like, does this code have bugs, for example? Yeah.
I wanted to say that it's very using other natural examples. It is the natural example. So for chess, for instance, the top chess players are coached by inferior chess players. Yeah. So it's interesting. Lots of
Thank you for the talk. So you mentioned the tasks involve a combination of NLP and vision tasks. I wonder, do we believe these tasks are already at a level that is challenging for human? And do we need to validate progress on tasks that are actually much harder?
Yeah, I mean, definitely these are not challenging to humans. So all of the tasks that we considered are like very standard NLP datasets. And I mean, the reward modeling task is a very strange task. Like it's actually can be hard for humans to tell which one of the computations is better. But I think, yeah, like the point is that it's just a problem that can become quite important at some point, like once the models are smart. But then how do we start making progress on it now is very unclear because we don't have those models yet. And so we study this like toy setting pretty much. Yeah.
I wonder how much the weak models agree. So the weak models have worse labels, but if I were to train through copies of GPT-2, how much would we agree on those labels? And is there any relationship between the agreement between weak models and how much PGR we get?
Yeah, I think the closest we have to that question is like we actually have points on these curves that are like GPT-2 trained on GPT-2 weak labels, which is not training the GPT-2 twice, but rather like we train the GPT-2 and then we use its labels to fine-tune another GPT-2. And yeah, you can see that it's these points here. You can see that they are still not at 100% actually, but like 95 maybe for the NLP tasks. Yeah, I think in general, it's quite surprising how hard it is to get high agreements in like distillation settings, in particular in this setting.
So this focuses on having a weak model supervise a strong model. Is there any, I guess, value in having a model just supervise itself?
I mean, so for this work, like we use this as an analogy for humans supervising strong models. So we don't really care about weak models supervising strong models, at least for now. We care about this as a way to start studying the question of humans supervising superhuman models. And yeah, I think in general, for sure, like for things like self-improvement, we want the models to supervise themselves and kind of in RL reinforcement learning loops. But yeah, for this particular work, this was just an analogy for humans supervising strong models.
Are there any like alignment issues with the self-improvement?
Yeah, I mean, of course, yeah. For if we imagine, we have models that improve by themselves, that is kind of difficult from the alignment perspectives because, yeah. I guess we want to, at some point at least, inject human preferences at least into the process. Yeah.
I mean, so the point is that the weak labels are noisy in their bias. Did you go in and like try and kind of classify the weak labels as in this is the weak label being very wrong, and it is okay that we can't train the strong model to just like make mistakes? Have you tried to dig in and kind of see where the issues are happening?
Yes. So we have some experiments. I think we tried to do things like what you're describing. I think that actually we have a relevant experiment, but different from what you're describing, which is we are trying to construct the weak labels in different ways. So here, the weak labels are just coming from the weak models, but you could imagine, like, it's actually not obvious that that's the best analogy for humans providing the labels. For example, like we have more synthetic ways of constructing the weak labels. So for example, a very toy way would be if it just takes ground truth labels and add noise. That's actually the simplest setting. In that setting, if you train on enough weak labels, you get perfect generalization because the strong model just cannot imitate the weak mistakes. But then also the other option is extremely easy to imitate mistakes. So if you just like make the weak labels, the ground truth labels, but flipped always, for example, then that's easy to imitate, and then the strong model will just learn that. And then you can do everything in between those. So I think at least one of the important axes is like how easily imitatable the errors are from the weak model. Yeah, that was one experiment related.
So I was curious about the inverse scaling. So when you measure the strong student compute, I was wondering, so do you fix the model size by using more and more steps of backpropagation, or you fix the number of training steps by using a larger and larger student pool?
So here, each of the models corresponds to a different size. If each like point corresponds to a different sized model, but I think it's neither. It's also not a fixed data set size. So this is pre-training compute. This is not the compute that we spent during like the weak to strong generalization. This is the pre-training compute used to train the base models, and they are trained according to some scaling law. So I don't think they use the same amount of data for each model. Thank you.